Hello, everyone, and welcome back to Physical Geology 1403. Today is Lecture 4, Volcanoes! Yay! This is a continuation of what we learned last time we met about igneous rocks and intrusive activity. Volcanoes are the extrusive activity aspect of the igneous process. But before we jump into that, questions? Any questions at all about anything whatsoever? Shoot, doesn't even have to be geology related if you don't want it to be. No? Yes.
Do you know the snake's sex?
Yes, it's a male. Yeah, for
How
sure.
do you know?
The sexual organs.
Oh,
Yeah, so snakes have what's called a cloaca. Do you know what a cloaca is?
it's everything.
It's a weird way to put it, bro. But I see where you're going for there. A cloaca is one multi-purpose hole. Pee, poop, sex, all out of the same hole or in the same hole. Okay? That's how it works with snakes, birds, starfish, right? There's a whole lot of things that have a cloaca. All right? Except difference with starfish is they also eat with that same hole. So yeah, isn't that appealing while you're eating or drinking your breakfast right now? So when a snake is first born, it's difficult to tell what sex it is. But after a couple of weeks, it is large enough that you can investigate the cloaca in using certain instruments to figure out which sexual organs are in there. Okay. So yeah, I do know that Diablo is a male. I'll probably breed him at some point later this year. He's large enough. Normally you'll wait until your snake is about 1,000 grams before you try to breed them. Otherwise it might be dangerous because the females are a little larger than the males. So a female about his size, about his age would be about 3 or 4 inches longer than him and a little thicker. So because snake sex involves getting all wrapped up and squeezing and all that sort of thing, it would be dangerous for him if I threw him in a container with a female and he's not big enough to take it. He could actually die from that experience. So I've been waiting a little bit until he's old enough. He's about 2.5 years old at this point. So I think he's about there. Good question. What else? How's that for a first topic of the day? Snake sex. You all awake now? Okay. Yeah. Go home and tell that to your parents. Watch what happens to me. All right. Well, announcements. What do I have by way of announcement? This is lecture 4. This is the halfway point in module 1. So after 5, 6, and 7, we will be preparing for our first exam. So you're about halfway there. Hope you're learning what processes, what works for you to take good notes. I hope that you have found that. They are going to come in very useful. And let's see, what else? I can't think of any other class-wide announcements I may need to say, except that for those of you here in the classroom, make sure you're keeping up with the other assignments, discussion boards, and lab and all of that. Those of you that are taking my class online, make sure that you are participating in these lectures on GoReact sufficiently, matching those 6 criteria that I've talked about before. And also, the lab work. And if anyone needs tutoring, please reach out to me. No one has yet, except I've had one online student who has come to visit me twice now. But please feel free to reach out to me. If we need to meet virtually, we can. If we want to come in person, we can do that too. If you just have a few questions and you want a phone call, I'll be happy to do that. If you need to come in the evenings, I do have an evening tutor at the Learning Resources Center. The schedule I sent out in an announcement, I believe, last week. So refer to that if you have forgotten when she is available. Yeah. Should we get started? Last chance? Well, not last chance. You can ask a question anytime. But shall we start? Mm-hmm. All right. So volcanoes. What do y'all know about volcanoes?
Magma is underground.
Magma is underground. Cool.
It produces gases.
Produces gases.
Is it essentially a mountain with a hole that allows inner stuff come out?
A mountain with a hole that allows inner stuff to come out. Sure. Yeah. There's that kindergarten definition that I asked for the other day, right? You're learning. Good. Okay. A volcano is just that, a conduit that allows magma to come up to the surface. This magma being pushed by various forces, including pressures and gases. But we'll talk about all that today. Okay. This is Mount St. Helens. Y'all ever heard of Mount St. Helens? Mount St. Helens is a large stratovolcano of the type that you will learn later on in this lecture. In the West Coast, over on the West Coast, it exploded. It erupted May 18th, 1980. It was before my time. Oh, I know, so long ago, right? I have actually a vial of Mount St. Helens ash here. So this explosion was so violent that the ash went 18 kilometers up into the atmosphere and fell as far away as Oklahoma. It removed the top 400 meters of this volcano in its eruption. Now, this is obviously before and after, but what do you notice about these before and after pictures here? Does it look like it just exploded out the top? No. No, what happened? Yeah, it blew out the side too. This is fairly atypical. Most of the time, yeah, volcanoes erupt out the top or near the top, where the vent is. We'll talk about the anatomy of a volcano in a little bit. But up there where at the top, there's a vent up there where the typical eruptions would take place from. Look at how much mass was removed in this eruption. It was incredibly violent. Now, leading up to this eruption, a gentleman by the name of Frank Johnston was sent to the volcano by the U.S. Geological Survey, the local U.S. Geological Survey office. For those of you that don't know, the USGS is the department of the government that is in charge of monitoring geological threats, environmental factors, resource development, things like that. So if you need someone to approve a new mine, you need the USGS to, basically sign off on it. If there's a volcano that is fixing to erupt, the USGS is going to be monitoring it. Anywhere that has earthquake activity, the USGS monitors all that. Okay. Also with water, groundwater services and purity and stuff like that, they monitor all of that as well. Anything that's related to the geology of the U.S. and the way that impacts the citizenry. So they sent this scientist, Frank Johnson, out to watch the volcano because there had been some signs that it may have started gearing up for an eruption. They attempted to evacuate the area around the volcano when they were sure that it was going to erupt. Most people left. Some people didn't. 58 inhabitants of the area did not leave. So Frank Johnson set up his trailer on a hill near the volcano so he could watch it. He had his lasers pointed at it. He has all his instruments, his seismometers. He was monitoring it. The day of the eruption, he noted and sent back that the sides of the volcano had expanded 6 feet. All these pressures building up inside of this volcano had caused the sides of the volcano to expand outward, like blowing up a balloon. 6 feet. And then it erupted. Now, unfortunately for Frank Johnson, it didn't erupt out the top. It erupted out the side. And he had just happened to set up his trailer on this hill that you can just see the part of over here. So the last thing anyone ever heard from him was a radio message to the USGS headquarters saying, "Control, control, it's happening." And then that was it. They didn't find his trailer until the mid-2010s. It was buried in mud. Obviously, nothing left of him. So he and 58 other people died in this eruption. Pretty bad. In our modern society, where hopefully we should be able to tell when these things are going to happen and get people out. You can't always account for the people who just don't want to leave, though. How many of you were born after 2005? Most of you. So you don't know personally the stories of Hurricane Katrina, but I'm sure that you've heard some stories about that. Massive 2005 hurricane swept through New Orleans, totally wiped away a bunch of people because they flat out refused to leave. Billions of dollars in damage, tons of people died. There's always going to be people that refuse to leave, either because they don't believe it's going to happen, or because what they have there is worth risking their lives for, even though by being there, they won't be able to save anything. So this is the sort of thing that we want to pay attention to. It's the sort of thing we need to learn more about. It's the sort of thing that matters. Okay? Geology isn't just about finding minerals to exploit and improve civilization. It's about watching out for other people from things like this. These things are going to happen. We will never, ever, ever be able to stop something like a volcanic eruption from happening. But what we can do is learn the right places to live, right? If people hadn't settled around a place like this, then no one would have died from it. Also, if people are going to insist on living in these places, then we need to make sure we have the right science and the right technology to be able to help understand when the problems may show up and get those people out. This eruption had the energy of 1,600 nuclear bombs, equivalent to the type dropped on Japan to end World War II. That's a lot of energy, all released in this huge cataclysmic eruption. Now, where did all the mass go? Blasted up into the atmosphere. Imagine flaming chunks of rock and debris and lava and ash chunk falling down. What do you see in this before picture that you do not see in the after picture around the volcano? All those trees, gone, flattened, carried away, immolated, annihilated, burned, vaporized, right? It's all gone. A lot of those forests have come back. They're not nearly as tall as they are here. You know, it's only been, let's see, 1980, 45 years, right? It's only been 45 years. A lot of these trees take maybe 100 years to get that big, okay? Do you remember the Mount St. Helens eruption? I'm sorry, I don't know how old you are.
I'm 48.
You're 48? So you were 3 years
I'm
old.
as old as these rocks.
You were 3 years old when it happened then, right? Because it was 45 years ago. So this is, unfortunately, Mount St. Helens, while being one of the more recent powerful eruptions, Mount St. Helens itself is actually fairly typical of a lot of the volcanoes that we have around the world. Meaning that this type of eruption, its violence and its destructive capability and killing capability is a threat in a lot of places, okay? This is Mount Tambora in Indonesia. You ever heard of Mount Tambora? Mount Tambora is what's called a supervolcano. Have you heard that term before? Raise your hand if you've heard supervolcano. Usually in reference to what? Yellowstone, exactly. There are actually only 2 active supervolcanoes in the world right now. Yellowstone and Mount Tambora. There are 26 of them, but the other 24 are inactive or extinct as far as we can tell. The last time Mount Tambora erupted was in 1815, and it created a cloud of ash that went up into the atmosphere and covered so much of the world that it extended winter for that year. Almost the entire year was winter, and it killed crops in New York across the other side of the planet. Okay? It affected industries and economies planet-wide. It was this event that caused a lot of people, a lot of scientists to realize that these sort of things are really worth studying, looking into. Okay? Events like this, imagine you're living in New York and it's just like the sky is dark and you have no idea why there is this really long winter and what's the stuff falling from the sky, you know? Why is it so dark for most of the year? And then a few years later, you hear about this massive volcanic eruption in another place in this chain of islands that you had only heard of and that maybe you thought were a myth or maybe you had never even heard of before. And that's what did it. People start paying attention, right? So there is great potential for worldwide catastrophe from these events. Yellowstone being one of those. We will talk about Yellowstone later on in this lecture today. So we've got a couple of different types of volcanic eruptions, right? We've got our more violent, explosive type eruptions like this. right? This is kind of a small scale version of what Mount St. Helens represented, okay? And then we've got our generally more calm or calmish, if you'd like, style eruptions like this, what you see in Hawaii all the time, where the lava just gets spat out of the volcano. It's just like, have you ever put mac and cheese on your stove, but you left the stovetop a little bit too hot, and so it bubbles up, and it's like you don't even know that it's happening until you're like maybe you're distracted on your laptop or your phone here, and you turn around and all the water is bubbling up and it's making a mess on your stovetop. Definitely doesn't happen to me all the time, right? I have 3 kids. I make mac and cheese a lot. Sort of like that, where it just kind of like overflows and bubbles out and gets spat out the top of the volcano. Less explosive, right? Definitely less violent, but it's still getting that lava, that material up and out of the volcano. Now, the number one controlling factor for volcanic explosivity is, in fact, the viscosity of the material inside of the volcano, the magma. Why would viscosity matter so much? Well, let me show you a few examples here of a few liquids that you're familiar with at this point. Here's some corn syrup, and here's water. Tell me the difference between them.
The water moves faster.
Water is faster because it is less viscous. Good.
I was trying to remember how to say it.
Yeah, no, that's fine. Yeah. Now tell me something similar between them. We'll play them again. Bubbles. They both have bubbles. The difference being the bubbles in the water are rising up to the surface and escaping back up into the atmosphere, right? Why? Because the water is so non-viscous. The bubbles in the corn syrup, they get stuck. They can't move. When my fluid is non-viscous enough to allow gases to escape, the pressure doesn't build. But if the gases can't escape and they just build and build and build and build and build, then what else is increasing? Someone say that louder. Pressure. Thank you. Pressure is continually increasing, which means that the more pressure I have, the more violent my explosion will eventually be. You remember that example I gave the other day of popping open that root beer, right? What if instead of just popping open the root beer, I shook it first and then I popped it open? Right? 2 different reactions, same scientific principles, but the pressure in one has increased because of the amount of gas buildup. By shaking it, I've aggravated it, created more gas bubbles, and then out it goes. Okay, same thing with a volcano. So the biggest controlling factor on the explosivity of a volcanic eruption is, in fact, the viscosity of the magma, because the viscosity of the magma determines how easily gases can escape. Yeah, sure. Now, what controls the viscosity? This is kind of a callback to what we discussed last time. You can't see it. It's not there. Huh? Good. You remembered that, didn't you? Silica content. Good. Why is silica content controlling viscosity?
Because tetrahedrons.
What about silica tetrahedrons? They form,
Crystals.
I mean, they do eventually, but they form first. The silicon tetrahedrons are the bonds that form first in magma, right? We learned that, didn't we? So if that is true, and my magma has more silicon in it, then I'm going to have more silicon tetrahedrons forming earlier, binding up my magma, making it more viscous. Okay? So more non-viscous magmas are going to be those depleted in silicon, free silicons. Less silicons, which are also those richer in. Remember that inverse relationship I talked about? The inverse relationship between free silicon and something else?
Viscosity?
Viscosity is the product of this, but there's an inverse relationship between the amount of silicon and the amount of feel free to look at your notes. Yell stuff out. I promise I will not make fun of you for a bad answer.
Water.
Not water, but thank you for giving me an option. Iron and
Magnesium.
magnesium. Yes. The inverse relationship between the iron and magnesium and the silicon. It does this. Remember those scales of justice I talked about? Right? So if I have a non-viscous, silicon depleted magma, it's going to be rich in iron and magnesiums. And we call that mafic. Remember that? That's the composition. Mafic magmas are less viscous. Felsic magmas, therefore, are more viscous. Okay, now just by connecting these dots, all of this stuff which you learned last time we met, now you can tell me which composition of magma makes the most explosive volcano. And which one would that be?
High in iron, mafic.
But explosivity is tied to viscosity, and viscosity is tied to the amount of silicon. Felsic, you said? Who agrees felsic? Ah, music to my eyes. Since none of you are talking, I guess. Okay. Good. Felsic magmas make the most explosive eruptions. This is something that will come up more later. Also, temperature. Temperature is also tied to viscosity. Why would that matter? Why would the temperature of my magma matter as far as the viscosity is concerned?
Because the heat is building up the pressure and making it.
It's not so much building up the pressure, but yes, the heat is doing what to it? Yeah.
If it's hotter, would it be less? Would it flow easier?
Yes, the hotter it is, the more it'll flow easily. But why? What's it doing chemically?
It's energy. It's heat.
Yeah, the energy is.
Exciting it.
Yes, it's exciting it, and therefore what can't form?
Bond.
Bonds. The hotter it is, the less of the silicon tetrahedrons are forming. So even if I have a felsic magma, if I keep it hot enough, it still might be pretty runny. Problem is, the felsic magmas tend to form closer to the surface. Closer to the surface, the colder the temperatures are. So that doesn't happen a lot. But it is a factor to make note of. Okay? And then finally, volatiles. What does that mean? Generally gases. Extras that are in the composition of my magma. Mostly water. Most volatiles in magma are water. The amount of gases that I have produced will influence the pressure that builds up in my magma. Okay, so these are the three main factors on the explosivity of an eruption. Okay, so why do these eruptions happen? Well, here we have our mantle crust, right? Here's our crust, here's our lower mantle, here's our upper mantle. We get hot material that rises up here. These plutons start making their way up through the crust, making their way up to the surface, okay? And then we've got this magma chamber underneath the surface, and then underneath the surface, bless you, there is going to be a conduit that chews its way up, and that conduit eventually becomes a volcano. Okay, cool. Magma chamber, conduit, volcano, comes out of vent, bless you. So, as pressure is building up in our magma chamber, there's only one way for it to go, out. Eventually, the pressure that builds up into my magma chamber will overcome the opposing force keeping it down. Normally, the weight of whatever rock is sitting on top of it. Generally, the dried up, crystallized remains of the last volcanic eruption, plugging the hole, so to speak. Okay? Eventually, the pressure will overcome that force, and then, boop, pop the cork. Now, watch this video and tell me what the first thing that comes out of this bottle is. What was it? Gas, and then that foamy, aerated, gas-rich fluid. Okay? And then underneath of that is going to be the non-gas-filled fluid as well. Okay? Same principle is true for volcanic eruptions. The first pop the cork, gas. We'll talk more about that gas in a minute. After that is that gas-filled material. Okay? Talk about that later too. And then the runny material on the inside, the lava flows and all of that stuff comes out next. This is drone footage from Iceland taken last year. There was a volcano that erupted in Iceland called Mount Fagradalsfjall. They flew hundreds of drones over this thing. This is the only one that made it out intact, and you'll see why in a second. But look how fast that that lava's flowing. Yeah, isn't this beautiful?
Cutting it close.
Yeah, you can see why this is the only drone that made it out.
Because they were driving them stupid.
Exactly. Like, why
They
not?
wanted the best shot. They wanted the money shot. A guy named Bjorn Steinbeck captured that one. I follow. He's a great follow on Twitter or X, whatever you want to call it. Okay, he puts stuff like this up all the time. He does thunderstorms. He's there in Iceland. Iceland is probably my favorite place in this entire planet, by the way. I tried really hard to live in Iceland. I tried really hard to convince them that they should open a gold mine because I guarantee that there's gold in Iceland. I was like, listen, you have a lot of the same volcanology, sort of hydrothermal activity here that I studied in Nevada to find gold out there. So I can find you guys some gold. And they wrote back this. There's only one mining company in Iceland. They wrote me back and they said, yeah, we're sure you're right. The science sounds good, but it would take about $5 billion to open a gold mine, and we don't have that. So sorry. And I'm like, darn it. Otherwise, I would absolutely love to live there. Fantastic. It's a geologist's playground. You got volcanoes, you got glaciers, you got vast fields of lava rock. It's fantastic. All right. I spent a week there back in 2017. Absolutely loved it. Okay, so that type of eruption, not terribly explosive, right? It's just kind of like getting spat out like blah, 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 out the top, right? What composition would you guess that lava was?
Mafic,
Why mafic?
because it was runny.
It was very runny. Did you see how fast it was going? It was going pretty fast, but also, here's a good indicator. What color was the rock around it? It was black. So the crystallized volcanic rock that was made as a result of this volcanic eruption, rich in dark silicates, aka we're probably looking at a mafic material, right? Good. Okay. We talked about the calm versus explosive. The calm eruptions, generally, those will happen when the magma chamber simply fills to overflowing versus pressure builds up to the point where there's an explosion. Okay? So it's like oozing out onto the surface. This is what happens in Hawaii. This is what happens in Iceland. This is what happens in a lot of these places that are fed from mafic magma sources. Now, about 90% of all the material extruded at the surface is going to be mafic. Justify this. Tell me why. Why would this be true? Yeah.
Because mafic stuff is like extrude. You said extrusive, right? No.
You can have extrusive and intrusive in mafic rock.
But isn't.
But right now we're talking about extruded. You're right. Things that come out at the surface. We're talking about volcanoes today. I love where you're going with this. Try and follow your thought through.
Because it cooled like further to the surface?
Well, that's what makes it extrusive,
Yeah.
right? I'm asking why 90% of all extrusive material is mafic. What about the density of it? Where do we find it? Denser things tend to be lower, right? Less dense things tend to be more buoyant over, or even if they're just near, the more dense things. Do you remember we learned the difference between the density of oceanic and continental crust? Which one's denser? Oceanic. Why? Connect the dots. Why is oceanic crust denser? It's more iron rich, making it what composition? Mafic. Oceanic crust is mafic. Okay? It is denser, which is why the oceans are on top of that instead of on top of the continents. Right? I saw a very intriguing movie trailer last week, actually. Sorry, first tangent of the day. This family is out on like a fun sightseeing boat trip or something, and they're asleep in the boat at night, and all of a sudden, like the boat is just rocking back and forth, and it's like there's this huge storm. This looked like a low budget movie, right? And then in the morning they wake up and the boat is on the bottom of the ocean, but the water's all gone. And throughout the course of the trailer, this isn't really a spoiler because you can look up the trailer and figure this out too. They make radio contact with someone else who was in a submarine who says, yeah, something happened. We think it was aliens, but all of the water that was in the ocean got taken out like onto the continents. Like the aliens somehow took all the water out of the oceans to shove it onto the land and kill everyone. So only people that were out on the ocean at the time that happened survived. And they have to somehow make it to this guy in his submarine before the water comes back. It's a very intriguing movie idea. Totally ridiculous, but very intriguing. The whole point is, most of our planet's covered in water, right? Water sits on top of the continent of the oceanic crust because the continental crust is more buoyant on top of the mantle than the ocean crust is. And therefore, the low points in the crust are where we have ocean. That oceanic crust. Okay, you following this logic here? Cool. Now, about 9% of all of that extruded material is intermediate. That's where we get a lot of our mountain ranges, right? And then about 1% is felsic. Why would we have such a low amount of extruded felsic material?
Because it's only at the very top.
I love the idea, though. It's not because the pressure shoots it straight up. What do we know about felsic magma? It's what?
Silica rich.
It is silica rich, making it very... Say it louder. It's very viscous. Good. How easy is it for something viscous to flow? It's difficult, right? It's starting to bleh, but I don't want to start that over, okay? That's the official sound effect for corn syrup, by the way. It's bleh. All right? It doesn't flow very easily, which means we're not going to get a whole lot of it that gets pushed out into flows on the surface, are we? No, that makes sense. Okay. We good so far? Any questions about anything we've discussed? No? Good. Then let's learn some Hawaiian. We're going to talk about two different types of lava rock that have Hawaiian names. Why do they have Hawaiian names? Because they were studied in Hawaii first, and so people named it that way. So say it with me. Ah. You didn't say it. I'm looking at you. Say it. Thank you. Good. Now, why is this called Well, if you were a barefoot Hawaiian and you walked on this, what would you be saying? Right? I'm kidding. That's not actually why it's called that, but I like to say that joke. Okay? This is called It is chunky, blocky, sharp, jagged. If you had to guess, what would be the composition of this rock? Just based on looking at the color. Mafic. Yeah, very dark colored, blacks, reds, some oranges, right? This is mafic. That's also easy to tell because like all lava rock in Hawaii is mafic. It's an island made out of basalt. Okay, what we're looking at here is basalt. This is a variety of basalt called a'a because this is what basaltic lava flows will often form into. Okay, so it makes these tough, jagged blocks when it is a low temperature mafic lava flow that cools off the surface. Okay, it makes these jagged blocks. Go ahead and pass that around. Now, when you have a higher temperature mafic lava flow, you make more curvy, sort of ropey, less large holes. It makes this. This is called pahoehoe. Say it with me. Pahoehoe. Good. You've learned 2 Hawaiian words today. Don't you feel accomplished? It's only, what, 10 o'clock? Yeah, it's 10:12. Well done. Okay. So this pahoehoe, high temperature flows, mafic composition, still basalt, just like this one, but made from a higher temperature flow that cooled off and made these sort of smooth, ropey features. So this is an a'a flow, moving very slow. Why? Because low temperature, it's not moving very fast. It's a low temperature, but it's still getting pushed forward. And then these are very high temperature, fast moving flows, but on the surface, you can see they're cooling off with exposure to the atmosphere. And that's what makes this ropey textured pahoehoe. Okay, some other things that can form as a result of volcanism. Lava tubes. If any of you ever have the opportunity to go to Hawaii, highly recommend getting a lava tube tour. They're pretty cool. What is a lava tube? Lava tube is when you have a pahoehoe type flow, very hot, moving very rapidly, and perhaps it finds its way into maybe like a stream bed or some other low point where it's effectively making a lava river as it flows. What happens to the outer surface, the top surface? It cools off, as will the outer edges, effectively making a pahoehoe tunnel, in the middle of which is still hot enough for lava to flow away. As temperatures decrease, perhaps my volcanic eruption is winding down. There's not as much material getting pushed. There's not as much pressure to force it out. The temperature starts to decrease. The inside lava in this tube is no longer going to be hot. It's going to cool off, and therefore, we're going to form a'a inside of this tube. Jagged, chunky, blocky pieces of lava rock. And so we have a solid outer tube filled with jagged, chunky blocks. The next time my volcano gets ready to erupt and that cork gets popped and I get that burst of gas that comes out, that gas is going to find this tunnel and it's going to shotgun blast all that a'a out the other side. It's going to basically clear the pipe as a result of the physics here, leaving an empty tube. Now, assuming that my volcano doesn't then erupt again, just the gas came out, which happens all the time. Gases more often volcanoes more often release their gases in some way. It finds a release rather than erupting, far more common. Then I just have an empty tube, and that's what lava tubes are. And you can walk through them in Hawaii if you want. There are tons of them. They're really cool. Then we've got block lavas. Block lavas look like this. This is a field of lava rock where a felsic or intermediate lava cooled, crystallized, and then broke apart. Think of the best way I can describe this is, have you ever seen mud dry out? What does it make? Yeah, cracks, sheets. It breaks apart. As the water inside of it leaves, evaporates away, the mud starts to crack and form individual chunks and pieces. The same sort of thing happens here. As my felsic magmas cool off, and intermediate magmas some of the times, it's going to contract as it's making these solid bonds. As it makes these solid bonds and contracts, it's going to pull away from other parts of it doing the same thing. And so eventually, instead of having a solid layer of rock, a lot of the time what we'll see is, in fact, these fields of block lavas. And then there's pillow lava. Ooh, it sounds comfy. Okay.
Yeah.
Yeah. Burn your face off, right? But I'll show you in a second why it's called pillow lava. Let me set the stage a little bit here. When I have lava that is being extruded underwater, what's going to happen to the outer surface of that flow? It's going to harden really fast. Remember the word we used for that?
Quenching.
Quenching. Good. Okay. When my lava gets quenched, it makes that hard outer crust, but it's really thin. The pressure from the magma behind it is still going to shove through. It's going to keep pushing through this newly formed material, right? And it ends up making a sort of smooth, tubey, pillowy shape. So let me show you a video of this process. Soon as that hot lava gets exposed, it gets cooled, but the lava behind it keeps pushing forward, expanding out this pillow lava formation. That's what it looks like underwater. Pretty cool, huh? Yeah. Now, the gases in magma are the main factor that cause eruptions, right? Viscosity is going to build, but that viscosity is going to be a product of the composition. But the gases involved are going to be making the pressure that are the driving force behind an eruption. There can be up to 6% of the total mass of magma can be gases, dissolved gases that start to reform as it cools off. Now, what you see here in this pool of lava here are gases that are coming up to the surface. There's bubbles of gases that are coming up like boiling water and escaping, right? What if it's underground and the gas can't escape? It's all going to build and build and build until boom. Okay. During a volcanic eruption, a standard average volcanic eruption, there will be thousands of tons of gases that are released from that eruption every day. Most of it's water. Then there's CO2, nitrogen, sulfur dioxide make up the rest. So a lot of gas going up in the atmosphere. Not so much a tangent, more like a precursor to something we discuss in more depth in 1404. Do you ever wonder where our atmosphere came from? Earth didn't always have an atmosphere. What is the composition of our atmosphere? Nitrogen, oxygen, carbon dioxide, and a little argon and other stuff like that. But those are the three main ones. Does that sound eerily similar to what we're looking at here? Yes. As a matter of fact, we believe, strongly believe, there's large amount of evidence to suggest that our atmosphere exists because of the billions of years of volcanic activity that our planet has experienced. All those gases in our atmosphere are the result of billions of years of volcanism. Yeah. Cool, huh? What about our oceans? Where did all the water on Earth come from? Where would the ice come from? The what? Yeah, but where did the water come from in the first place? It probably was ice. A lot of it, we believe, came in the form of comets and asteroids that hit our planet early on. Okay? Most of the comets and asteroids that we see out in space right now are entirely, or a large part of them, are ice. H2O, water, is one of the most common, I believe it is actually the most common, three-molecule bond in the universe that we can see with our telescopes. There's a lot of water in space. It's just mostly ice, right? And space is cold, right? And so when there was a lot of comets and debris and all this stuff just floating around in space early on in our solar system's history, a lot of that impacted our planet. Our planet was a large gravitational force, so it pulled a whole bunch of it in on itself. A lot of that stuff hit. The water stayed, became evaporated water in our atmosphere, and combined with the water being, ejected through volcanoes, all of that coalesced eventually over time and made the oceans. Okay, so that's where atmospheres and oceans came from. Pyroclastic material is the result of volcanic eruptions. Perhaps you remember this. Pyroclastic is one of the textures that we learned about, igneous textures that are relevant for Lab 2. Pyro meaning fire, clastic meaning fragment or piece, right? That's where this word comes from. It is a piece of something that is the result of a volcanic eruption. This includes ash, right, which I have a little vial of here. I'll pass it around in a minute. Okay. Ash is anything smaller than 2 millimeters. That can come together to make a type of rock called welded tuff. Then there is lapilli, which is what you call it if it's between 2 and 64 millimeters, also known as cinders. And then there are bombs. Bombs are anything larger than 64 millimeters. We call them bombs because they're usually, camera, stay with me now. Camera. Hello. There we go. These are chunks of semi-melted debris that get blasted off the volcanic surface or from the interior and cool off as they are flying through the atmosphere. And because they are in a semi-melted state, they will often reshape themselves to be more aerodynamic as they fly through the air. Think of the same way as a raindrop will, right? A raindrop, you well know that characteristic raindrop shape, right? Well, these will often take on aerodynamic, smooth sort of shapes in the same process. This is a lava bomb. Now, when you picture in your head this eruption, just like that root beer, you've got your puff of gas, and then what comes after that? That foamy, gas-filled, material-y stuff, okay? Now, I already told you about one type of this called pumice. Where's my pumice? It's probably over there. Yes, there's a pumice. Okay. This pumice, this is the same one that can float on water. You go to the spa, they use it to take off your calluses, all that stuff, right? This is pumice. But what about if I have a mafic eruption? What would be made then? Sometimes you still make pumice, but a lot of the time you make its mafic equivalent, scoria. This is scoria. Notice that it is very similar to pumice, but what's the big difference here? The color, and the color is reddish, black, gray. Clearly, more light or dark silicates in this than there are in pumice, right? Even though it's filled with all those holes, this probably won't float on water, at least not for long, because it is still denser because of the minerals inside of it. Okay? Still doing good? Great. Okay, let's talk about volcanic structure. Most volcanoes have this generally cone-shaped structure, right? It's very characteristic. When you see that, you think, oh, volcano, okay? The sides of the volcano are built up by layer after layer after layer of eruption material, be that mafic or felsic, and ash. Eruption material and ash, eruption material and ash. Now, the slope of my volcano is very much dependent upon how far that eruption material made it. If I have a very non-viscous material, the slope of my volcano is going to be very low angle, because by being non-viscous, that material can get a lot further before it hardens, right? If I have a very viscous material, then it's not going to make it very far before it hardens and crystallizes. And so I'm going to end up with piles of material very near the vent, and I'm going to have very high angle structure. So just by knowing that, can you tell me what sort of composition I would expect in a low angle volcano? What composition of magma would feed a low angle volcanic structure? Huh? Yeah, but what's the composition? You're right, it would flow quicker, but what does that mean for the composition?
Flat.
What's the composition, though,
Oh,
of the magma that would feed a low-angle volcanic structure?
mafic?
Mafic, because mafic is more non-viscous, right? Mafic can flow further before it cools off, and therefore I don't have a buildup of material right next to the vent. Whereas with felsic, I get a very high angle structure. Okay, material that can't make it very far will make a higher angle volcano. That'll be relevant here in a minute. Okay, so then we've got our crater at the top where the vent comes out and deposits material. Every now and then it is possible that a crack could appear in our volcanic structure, allowing magma to come out of a different location on the surface. Okay, that's called a parasitic cone when it comes out on the surface. A fumarole occurs around the base of the volcano where the groundwater gets heated up to the point of steaming. And so you get basically steam vents that come out in the periphery of our volcanic structure. We call those fumaroles. Here's Mount Fagla dal Sfial again. You can see that cone shape. In the middle of our cone, here's our crater. The vent is connected to the conduit, going way down underground to wherever the magma chamber is for this structure. Now, yes, those are Icelanders. Mount Fagla dal Sfial was actually only about 15 minutes away from the Icelandic capital in Reykjavik. And so these are people on their lunch break just going to look at the volcano erupt. Pretty cool. Yeah. Yes, this is a very new volcano. So what you're looking at, this structure here, this depression, is an older volcano. Fagla dal Sfial is actually this whole thing. This is the newest cycle of eruption. It is a structure that has built up as a result of this eruption. Yeah. This particular volcano, I couldn't tell you. It's erupted a lot over the years. I don't know the original age of this particular one. Yeah.
I have a dumb.
No dumb questions here. I may give you a dumb answer though.
Like all the landscape, everything, the terrain, everything around us is because of volcanoes.
Here, where we live,
Like just on the planet.
in general,
Yes.
volcanism has played a major role in the formation of material, of continental material and oceanic material, yes. You'll understand more about all of that as you go through the semester, but volcanism is responsible for making all the igneous rocks, and obviously there's a lot of igneous rocks on our planet. A lot of those igneous rocks then weather down to make the sediment that makes a lot of the sedimentary rocks that we have. So in some way, all the rock cycles, you cannot have the rock cycle without this, right? So this is an essential part of it. Volcanoes being how it expresses on the surface, this sort of thing. The crystallization of magma occurs underground as well, like we learned last time, right, on Tuesday. What was I going to say? It had something to do with your question. Remind me what your question was?
If the terrain, the landscape.
Oh, sorry, I'm talking.
everything-
I'm sorry. What was your name again? Yes. Rain. Yes. What was your question again?
I was asking how old the volcano is.
Oh, I was going to talk about this. Okay, so back in, when was this? 2010, I think it was. Mount Eyjafjallajökull in Iceland erupted. Y'all probably don't remember that. Do you remember this? It shut down air traffic to Europe for about 6 months. No? Why would it shut down airplane travel around Europe for a volcano in Iceland to erupt? What does the ash do? You know what ash is?
Rock.
It's essentially vaporized rock. It is flash melted, flash vaporized rock. Now, when you melt it immediately and you cool it immediately, you make that glass we talked about. But what happens if it's also vaporized? You have microscopic glass crystals. That's what this is. That's what ash is. Microscopic shards of glass in the atmosphere. Now, an airplane engine You know how an airplane engine works, right? Pulls air in one side, and then the engine's blasted out the other side, right, to make propulsion. Well, when you pull in ash to an airplane engine, turns out that caking your engine parts in glass aren't good for an airplane. And so airplanes started falling out of the sky. And so they shut down air traffic pretty quick. So Mount Eyjafjallajökull did that, had that kind of impact across a significant part of the northern hemisphere for about 6 months. There is another volcano called Katla, not far from Eyjafjallajökull. We call them sister volcanoes. Why? Because they are often associated with each other in eruptions. Geologically, they often erupt with each other or around the same times. Katla is about 3 times bigger than Eyjafjallajökull. So they are watching it very closely right now because that one could erupt very, very soon. And there's actually a lot of glaciers that are sitting on top of it. So that would make things very interesting for the Iceland region to have all those glaciers melted as a result of a volcanic eruption. Yeah?
How much would those glaciers affect the eruption?
The what?
How much would the glaciers affect the eruption?
The glaciers affecting the eruption, and it would dampen it initially until the glaciers melted away. Ice can't stand up long to that kind of heat, right? So there's a lot of ice there, but it would eventually melt away, probably over the course of a few days. And then the volcano would be fully exposed, and then it would just erupt like it would normally. Yeah. Okay. Let's talk about the 3 main types of volcanic structures. We have shield volcanoes, the largest kind, okay? The wide angle, very long, very wide shield volcano structure. This is what Hawaii is. All of the islands of Hawaii are shield volcanoes, as is a significant part of Iceland are built up shield volcanoes. Then we have composite cones like Mount St. Helens and Mount Rainier in Washington, okay? Also called stratovolcanoes. And then we have cinder cones, which are the smallest type, but come with their own unique set of interesting traits. We'll talk about each of these. Starting with shield volcanoes. Hawaii. I mentioned that Hawaii was primarily made out of one particular kind of rock. What was that? Mafic. That was the composition, but what was the kind of rock? Basalt. Good. Mostly basalt, mafic composition. Thank you. Mafic being very non-viscous. Therefore, it can flow out further and longer before it cools off, right? Making that wide, low angle structure I talked about. That is a shield volcano. Bless you. I don't know if that was a sneeze. May have been a cough. Bless you anyway. Gosh darn it. All right, so we get layer upon layer upon layer upon layer upon layer upon layer of widely flowing basalt lava, making these layers of rock that eventually makes a very wide angle island. Now, Hawaii actually goes way further out underwater than you can see from the surface. As a matter of fact, it goes all the way to the bottom of the ocean, up to the top. Do you know what the tallest volcano in the world is? It's Mauna Loa. Yeah, actually, it might be Mauna Kea. It's one of those two. Why? Because it basically goes from the bottom of the ocean up to here, to the summits. Because that's where this volcano starts. That's where the layers got being started deposited, the bottom of the ocean. Do you know what the tallest volcano in the solar system is? Oh, you're very close, yeah.
Is it on like Mars?
It is on Mars. It is Olympus Mons. It is a volcano 3 times taller than Mount Everest. Can you imagine if a volcano so tall you can put 3 Mount Everests inside of it? It's on the surface. Yeah. It is a truly massive feature on the surface of Mars. Can you imagine? It is so tall that if it was on Earth, you would not be able to like breathe or even be exposed. You would need a spacesuit to be on the top of this volcano if it was on Earth.
With that volcano erupting on Mars, would it start to create an atmosphere?
Ooh, Mars did have an atmosphere. It did. It had an atmosphere. It had water. It had rivers. It had oceans. It had all of that for the same reasons that Earth does from volcanic activity, presumably. Here's the problem, though. Its inner core stopped moving. Do you remember I talked about this? Its inner core stopped moving, rotating because it cooled off, right? It cooled off and got kind of frozen in place. So it was no longer rotating. Without a rotating inner iron core, Mars didn't generate a magnetic field. Without a magnetic field to deflect a lot of the radiation from space, the radiation made its way into the atmosphere and stripped away all of the atmosphere. As the atmosphere went, so did atmospheric pressure. Water evaporates easier at lower pressures, and so all of the water on the surface eventually evaporated away too, leaving behind the barren, dry Mars that we know and love today. However, the features are still there that show us, that this was real. Volcanoes like Olympus Mons show us that there was volcanic activity to make that atmosphere and water. And then there are river deltas and sedimentary rock on the surface that show us that there were water processes. Matter of fact, our Perseverance rover that landed there about 3 years ago is in the process of collecting a series of samples, dozens of samples from around the edge of this river delta. And those should be back here around 2035, 2036. They'll return back to Earth, the first Mars rocks ever to come here. And if there are fossils in them, then we will know for sure if there was ever life on Mars. Because if there ever was life anywhere on Mars, it would be there where there was water. And that's why they're taking the samples over there. Okay. Cool. Okay, so that's a shield volcano. Cinder cones are very steep, small, usually short-lived, but also can pop out of nowhere volcanoes. Just to give you some context here, in Paricutin, Mexico, in 1943, a farmer was going out to his field early in the morning, and he noticed that there was a crack in the ground near one of his fields near his house, and there was steam coming out of it. He didn't know what to make of it, but he couldn't really deal with it at the time. He needed to go out to the far fields. So he spent the day out working in the far fields, and over the course of the day, he heard rumblings. It sounded like lightning, but there was no clouds in the sky. So at the end of the day, he goes back home, and he finds that this crack in the ground is now spouting fire and has formed a mound a couple of dozen feet high of glowing rock. His family's nowhere to be found. His house is abandoned, so he drives over to the nearest town. He finds his family there, but they have to evacuate the town because over the course of the next few days, a cinder cone developed on his property, and there was lava flooding the town in a few days. As a matter of fact, you can go online. They actually still have this. A lot of this town still has lava flows. You can look online. There are pictures of the town chapel, the what do you call it? The church, the local church, right? And there are lava flows almost up to the top of the building. And this came out of nowhere. Within a matter of a few days, the entire town was abandoned and filled with lava. And though this volcano actually only lasted for 9 years. It died in 1952, but when it died, I mean, it had already done a lot of damage. It grew 330 meters in 1 year. So it came out of nowhere very quickly, but then it also died relatively quickly. 9 years, that's like no time at all, right? At least as far as volcanic lifetimes are concerned. So the big danger with these is that they can pop up. Not really anywhere because they have to be associated with a magma body. They usually don't have lava flows with them, but they do come with a lot of heat. They're usually made out of scoria. That rock I passed around earlier that's kind of like pumice, but it's made out of darker material, right? So why does it have these steep sides if it's mostly mafic material? Well, because that scoria it's got those jagged edges, right? It's like trying to pile Legos on top of each other. You can make a pretty tall pile of Legos with pretty steep sides to your pile because all those edges are holding on to each other, right? Same thing with scoria. And so you get very steep sides to these cinder cones. And then the final type of volcano are composite cones, also known as stratovolcanoes. These are by far the most dangerous. Why would they be the most dangerous?
They have a big boom.
They have the bigger boom. Good. Okay, they've got the biggest booms. They have the biggest booms because they are fed by the most viscous magmas. Felsic and intermediate magmas feed these volcanoes. People also tend to live around them. A lot of these volcanoes form near convergent plate boundaries. These convergent plate boundaries are often coastlines, and people like to live on coastlines, right? About 70% of the US population, right, or somewhere around that, lives on or near a coastline. And so a lot of these volcanoes, in particular on the West Coast, are in those locations, which makes them dangerous because of proximity to people. A lot of the volcanoes in the Pacific Ring of Fire, which you've probably heard about, are composite cones. These come with lava flows, they come with ash clouds, they come with a variety of dangers, which I will now elaborate on. You want to hear all the ways a volcano can kill you?
Sure.
Yeah, let's do it. Okay, the first up is a pyroclastic flow. A pyroclastic flow is that first, so you pop your cork, right? Pop that cork, what comes out? Gas. That gas is incandescently hot and it's filled with ash. It's a cloud of gas and ash. And remember this ash, microscopic shards of glass. Even cold ash is dangerous, by the way. Even if you're nowhere near the volcano, if this is falling, you better cover your mouth. What do you think happens if you breathe in ash?
Pneumonia. No.
Pneumonia?
Something like that.
I mean, a very mild case of ash inhalation can give you pneumonia. You breathe a lot of this in, you breathe a lot of microscopic glass shards into your lungs. It slices up your lungs on the inside, and then you drown in your own body fluids.
Oh.
Delicious. Okay. But now let's get back to pyroclastic flows. This is the hot ash, right? With all the gases and everything. Okay. So these come out at a screaming fast pace. It's kaboom, and then this gas is just flowing everywhere. Okay. Pyroclastic flows can go 200 kilometers an hour if you're close to the volcano. They obviously slow down the further you get, but extremely fast, right? It's on you in no time. This is a video taken in Japan from a few decades back. That is a pyroclastic cloud. Yeah, run. He did actually get back. He did get in the car, and they got away. But the only reason they did is because you see this hillside here. So this hillside goes up and then down, and then the volcano's on the other side. So the volcano erupted. The pyroclastic cloud had to go up the side of that hill and then down the side of this. And so it lost a lot of momentum. So it was already going fairly slow here. I mean, this is still probably 40, 50 miles an hour, right? But it lost a lot of that momentum going over that hill. That's why they were able to get away. But they had been here in this town monitoring the volcano. The town had already been abandoned because they knew it was going to erupt. Let me play that again. Can you imagine that coming at you? By the way, this is about 400 degrees Celsius. This is instantly immolating every tree, every house, everything in its path.
So you could like feel the heat coming before he.
Yeah, probably. Yeah, at least a fairly good distance away. I don't know about that far away. Notice that he was wearing a heat suit, he was wearing a heat suit with breathing apparatus. He probably didn't need it yet, but he had probably been conducting some experiments on near the volcano before this. But yeah, so extremely hot. Every tree, everything in its path, instantly incinerated. The camera? Yeah, that probably too got destroyed. I think the video ends there because that's when they stopped to pull out the tape.
And run.
Yeah. Okay, now go. Right? You ever heard of Pompeii?
Yes.
This is what got Pompeii. And by the way, no one ever talks about Herculaneum, but that was the other town. When Mount Vesuvius erupted in 79 AD, the pyroclastic cloud swept through these towns at the beginning, in the middle of the night. Let me show you pictures if you've never seen pictures. Pompeii. People asleep in their beds, in their homes, immediately incinerated as the ash coated their bodies and filled in their houses from this pyroclastic flow. Their bodies were immediately incinerated, but stayed just long enough that as the ash was fusing to itself around them, it left the exact imprint of the position they were in as they died. Most of them probably didn't even realize what was happening. Most of them were still asleep. Some were holding loved ones. Some were holding babies. One guy was in the middle of getting up. Maybe he heard something. Maybe he just needed to pee. There's a dog scratching itself. Immediately. Instantaneous annihilation. Now, how do we have these imprints? Well, for thousands of years, remember, this is 79 AD. We're talking about almost 2,000 years ago now, right? This layer of ash fused, which we call tuff, right, stayed there until in the 70s, some people were drilling there, some archaeologists, and they were drilling down through the rock, and they found holes down in this tuff. They found voids, and they were like, what are these voids? And they pull out chunks of rock, and they were like, that looks like a face. And that's when they realized what had happened and how it had happened. And so we used, or I say we, that's the royal we, geologists, used instruments so that we could get sort of underground pictures, bouncing sound waves in and out of this rock, by the way. Okay, we'll talk more about that later. And they were able to see where all these voids were. And then they were able to drill tiny little holes into them and then fill them with plaster, let the plaster set, and then chip away the rock from around it. And that's how we get these positive impressions of the people and how they died. Anyone else want to hold them? You do? Pompeii. All right. That's a pyroclastic flow. Gas and ash burning everything in its path. Next up, we've got lahars. Now, when you have a volcano that is high up in the atmosphere, you're going to end up with a lot of what on it? What do you see on there? Water in the form of snow and ice. Thank you. Okay, snow and ice. You get a lot of it. Now, as my volcano starts to heat up, preparing for an eruption, what's going to happen to that snow and ice?
It's gonna melt.
It's going to melt. And where's it going to flow?
Down.
Downhill. Usually along the same paths that the water's already flowing. Most volcanoes have rivers that are sourced from the snow and ice that are already on it, and that melts at a consistent rate. Okay, so all of that melted ice is going to gush. It's going to flood downstream, picking up everything in its path. This is called a lahar. Trees, houses, bridges, cars, people, anything in its path gets picked up on its way downhill until it eventually loses momentum. Lahars are incredibly destructive. This is a picture taken, I don't know where, but you can see what the water line was like. Here is where the normal stream bed was, right? You can see where the water line was on these trees. There's a person for scale, okay? And look at the size of the trees that it ripped up along its path downstream, okay? These are trees that it would take 3 or 4 of us to hug around it together to get our arms around it, okay? That this thing ripped up. In Nevado del Ruiz in 1985, there was a volcanic eruption up in the Andes. The town wasn't really affected by the eruption. It wasn't close enough. But the lahar that came downhill out of the Andes as a result of this eruption killed 25,000 people. You don't even have to be anywhere near for this to happen. You just need to be downstream. For 8 months, I lived in a town on the edge of Mount Rainier. That's Mount Rainier right there, by the way. I lived in a town right next to the bottom of Mount Rainier called Ording. It's not far. And Ording was built on one of the rivers coming off of the volcano. It was gone on equal sides of this river. Half was over here, half was here. The river was right there. So to get out of Ording, there were 3 ways out. You could either go along the valley following the river. You could go up the volcano and around it, or you could go up the side of the valley and out. But to get up the side of the valley and out, you had to cross a bridge over that river. On the first Monday of every month, Ording had what they called a Lahar drill, where every siren in town went off. If that sounds annoying, imagine it going for 10 minutes. Okay? Now, the whole point is, it's supposed to be a drill where everyone in town grabs their stuffs, grab your wife, grab your kids, right? You grab everything, and you get out of Dodge. Because this town of 8,000 people has about 10 minutes, give or take, to get out of town before a Lahar coming off of Mount Rainier wipes the town off the map. How many people do you think practice? 0. Every first Monday of the month, the sirens go off, and nobody does a thing. Why? Because 8,000 people know that they're not getting out of town in 10 minutes. There's not a chance. Especially when you consider the only viable way out of town is that one that goes up the side of the valley. You don't want to go down the river valley when there's a Lahar coming. You don't want to go up the mountain towards it. The only way out is that one way up the side of the valley, and 10 to 8,000 people aren't getting across that bridge in 10 minutes. So no one bothers. So it's this sort of thing that we'll hopefully try and avoid in the future by understanding these threats before they become a real problem, right? By the way, you know what's further down that river? Do you know what city this is? That is Seattle. Seattle is built on top of 6 previous Lahar deposits. Literally on top of them.
Sounds like a bad
Yeah. So if Mount Rainier ever does go, Ording goes first, and then about a half dozen other towns along the way before eventually half of Seattle is wiped out. Yeah, they didn't know this when they built there, but now we do, so we pay very close attention. Mount Rainier is probably one of the most watched volcanoes in the world for a couple of reasons. One, because it has such a high population that's in danger if it ever does go off. And 2, it's also one of the few volcanoes where the magma chamber is ridiculously close to the surface. It would not take that much for the magma chamber to actually go a little bit further up into the volcano. And if it does, look at how much ice is going to melt off that sucker. It's going to be a big Lahar if that ever happens. It's not an if, it's a when, honestly. Yeah?
The other town you mentioned, where a Lahar happens, they're all screwed.
Yeah.
Are they able to track the volcano and know when a Lahar is coming?
Right. Well, this is what I just mentioned, right? That's one of the most watched volcanoes on Earth right now. I believe there's actually a satellite that watches that thing. Okay. But what are some ways we can monitor it? We talk about this a little bit later on, but we can use lasers to check if that ever changes in size, right? We measure the gas output of all the vents on and around it. We have temperature sensors like infrared and all of this that are pointed at it. We have all these different sensors and people whose jobs are devoted to watching Mount Rainier and other dangerous volcanoes, specifically so that we can give them as best a warning as we can. This is something that we'll come back to here in a little bit. Yeah.
Is there any man-made? Is there something that we can do? Like, let's say if that actually goes up to slow down the eruption.
I mentioned this earlier. There's absolutely nothing we can do to stop a volcanic eruption. Not a darn thing. Have you ever watched that old, I say old, it's as old as I am, the early 90s animated Hercules movie that Disney made? Yeah. So good. It's one of my favorites. I showed it to my kids for the first time a few weeks ago during the break, and they loved it. Made me so happy. You mean Hercules? Yeah, that's so good. At one point during the montage of him doing all his heroic stuff, there's a volcano erupting, and he takes a giant rock and then puts it on top of the volcano to stop it. That wouldn't stop it. It would just blow out the side. It's just the pressure needs to be released, and it will be released one way or the other, right? So no matter what we could do, physics happens. I need to make bumper stickers. Physics happens, right? It's going to happen no matter what we do. So no, there's no way that we would be able to stop it. You'd buy it? Okay, good. I have a t-shirt idea. It's so nerdy. You guys are going to love this. I've wanted to do this for years and I never have. So the genus for starfish is Asteroidea. That's the group that they're in. Excuse me. That's the group that they're in. They're in Asteroidea. Okay. And so I want to make a t-shirt that's got like on the foreground, it's got like dinosaurs looking up at the sky, and there's a giant starfish falling out of the sky. Only biologists and paleontologists would really get it. It's like they're about to be killed by a giant asteroid, right? Only a few people would get it, but the best t-shirts are the ones that only a few people get, right? Anyways, okay, so that's a lahar. Now let's talk a little bit more about some of the structure of volcanoes. Now that we've learned a little bit about more what they can do, let's talk about some other things. Calderas. A caldera forms as a result of the eruption. Now, calderas can be very large, or they can just fill in the top of your volcano. If it's just like a little minor eruption, it might just be about the top of the volcano, just wherever the last little boop was, whatever got popped off during the last eruption. But there are some truly massive calderas. For example, Crater Lake. You guys ever been to Crater Lake, Oregon? I got a picture of it right here. It's falling off my wall, it looks like. I need to get up there with a ladder and fix that. This is Crater Lake. Why do they call it Crater Lake? Because Crater Lake is what was left of a gigantic volcano that in the process of erupting, it was such a violent eruption that it completely destroyed itself. Blasted the entire thing to smithereens, leaving literally a crater in the ground. Yeah, you may. Okay, and that crater filled with water, eventually making Crater Lake. Oh yeah, there's fish in there. Yeah. It's a fun place to go. It's not very unique there either. This happens all the time. Whenever you have pressure that builds up so powerfully that the eruption just annihilates everything above it, you end up with a big old crater. We also call these calderas if they're big enough, the most famous of which is the Yellowstone caldera. See, I told you we talk about Yellowstone, not the TV show. I've been told so many times I need to watch that show. Yeah, I hardly have time for the shows that I'm truly, genuinely interested in watching. I did watch Game of Thrones. It was pretty good. I enjoyed it. I don't know. I don't know about recommending it, but it was fun. It was a fun watch if you're into fantasy, which I am. Okay, if you like dragons, it's really cool. All right, now Yellowstone itself, as I mentioned, is a supervolcano. Why do we call them supervolcanoes? Because of their size. The Yellowstone caldera is 15 kilometers across. If you ever go to Yellowstone National Park, the entire park is the caldera. That's how big this thing is. Were Yellowstone to erupt today, we here would be in trouble. About half the United States would be in trouble, depending on prevailing wind direction at the time. Utah, Wyoming, Montana, the Dakotas, most of those places would need to be evacuated. Anywhere nearby the volcano is absolutely destroyed. The town where I went to get my undergrad degree, my bachelor's degree, would probably be destroyed. It's about 4 hours from Yellowstone National Park. It would be totally destroyed. Half of the United States would be blanketed in ash within a matter of a couple of days. The rest of the United States, plus Canada and Mexico, would be covered in ash within a week. Pretty much our entire half of the planet would have ash falling on it after that. Yeah, it would send us into another mini ice age. Now, how many of you have heard the big old headline saying Yellowstone overdue for eruption? You ever seen those? Yellowstone due to erupt. Yeah, I got a few head nods. This is the problem with people. I say the problem. This is one of the problems with people. We like, what? Oh, yeah, careful. He would too. He would go in your sleeve. People they're drawn to what is the most attention grabby thing. When people take big headlines, like make big headlines about that, I call it sexy science. It's not necessarily true. It's just what grabs your attention and makes you look, right? It's true for dinosaurs more than anything. No one's really interested in the 100th, ceratopsian that doesn't have cool frilly horns. But as soon as you say new tyrannosaur discovered, everyone looks, right? Because everyone loves Tyrannosaurus Rex. When you make a headline that says Yellowstone volcano due to erupt any day, everyone's going to look at it. But they don't bother to look more than surface deep. Here's the problem with saying something like that. It's based off of the law of averages. Do you know what an average is? Someone explain to me what an average is.
The likelihood of something happening.
Is it the likelihood?
How many times it's happened?
How many times a thing has happened? Sure, in this case, the volcanic eruption. And then what's the other factor? The amount of time over which those events occurred. So if I have a volcano that erupted 1 million years ago and that volcano also erupted 10 million years ago, there's a 9 million year gap and 2 events. And so the average would be, it's 9 divided by 2. 4.5, thank you. The average would be 4.5 million years. And so just using those 2 points of data, I would be able to say, based on the law of averages, this volcano erupts every 4.5 million years, right? But what if the eruption before that was 500,000 years? What if the eruption before that was 100 million years? Averages only takes into account the data set that you put into it, right? So to say Yellowstone volcano erupts every 600,000 years, and the last eruption was 750,000 years ago, sure, based on that amount of data, yeah, I guess we are overdue based upon a man-made perception like averages. But guess what? Nature doesn't care a whit about averages. Nature goes when it goes. The last eruption before that was 1.2 million years. The last eruption before that was 2.1 million years. The last one before that, 2.3 million years. The law of averages is a man-made construction that we can't really apply realistically on top of nature. So yeah, these headlines say, sure, we're overdue from the average. But that is by no means saying that it's going to happen anytime soon. Yellowstone could erupt in 1 million years. Yellowstone could erupt tomorrow. Okay? That's the truth of it. I just need to point that out. Next time you see one of those articles, shake your head and say, silly journalists. All right? But then also, yeah, you and your sexy science. Science is sexy, by the way. Just when it's done right. Okay. Fissure eruptions. These are what happen when you don't have one conduit that just chews its way up to the surface. It's not a tunnel. It's more like a crack in the ground along which lava comes up to the surface and is expressed, okay? So this is a fissure. So you don't really get a volcanic structure built up. You get more of a plateau, okay? A shelf of lava that builds up on top of itself, okay? So these make basalt plateaus, which look like this. There's a lot of these in the American Midwest, okay? Idaho and Montana have a lot of really thick basalt plateaus underneath of the surface, okay, that people live on top of now, okay? So this is what basalt looks like, just flat layer upon flat layer of built up lava. A lava dome is the rebuilding of a new volcano on top of an old one. So here we have Mount St. Helens again. This is a closer up view of the one that we saw earlier, okay? Mount St. Helens, and what do you see in the middle here? Yeah, look at that tiny little baby volcano. It's so cute, right? We have a tiny little baby volcano building up in there. This is a lava dome. Think of that as the plug, the new cork on top of the conduit. And every time there's a tiny little eruption, it adds a little bit more mass to this lava dome. Eventually, this lava dome, if allowed to grow, will fill in this empty space in Mount St. Helens, given enough time. Look how much it's grown in 45 years, right? Clearly, there's still material getting pushed up to the surface, a little bit at a time, but it adds. Give it a couple hundred more years, there may in fact be a new larger volcanic structure inside of the old one. Yeah.
So let's say that one overtakes Mount St. Helens, would they have to change the name?
No, there's no reason to give it a new name. It's in the same location, right? The only reason why we would change this volcano's name is if Trump wants it to.
Oh my God.
Definitely not. Yeah. I mean, I'm totally fine calling it Denali, just for the record. I'm cool with that. All right. Huh?
Junior.
Call it call it. Oh, this one? Yeah, we could call this Mount St. Helens Junior. Yeah, we could. Yeah. It might grow to resent that over the course of its life, though. So we probably, it'll just be a constant reminder that it is the younger one. Okay. All right. Volcanic pipes. This is Shiprock, New Mexico. This weird, random structure in the middle of the desert in New Mexico. What the heck is that? Where'd that come from? It's a volcanic pipe. A volcanic pipe is when you have a volcano that is weathered and eroded until it's all gone away, but whatever crystallized inside of its conduit, right? Its conduit that fed that ancient volcano is now exposed at the surface. Shiprock and the other structures around it are what is left of the conduit all the way down to a magma chamber. Somewhere underneath of Shiprock is a giant magma chamber that used to feed the volcano that used to be here. And now the conduit is the only thing that's left. That's pretty cool. Yeah. There must have been a truly massive volcano there at one point for this to be what's left of the conduit, right? But it was so long ago that this is the only thing that's left. That is a volcanic pipe. Now, volcanoes don't just show up in places. Even the ones like the cinder cones that pop up what seem randomly have to be somewhere in proximity to a source of that heat. There has to be a dike that came from a magma chamber somewhere that then went on to form that cinder cone. But it has to have come from a magma chamber somewhere, okay? We actually, our area here used to be fairly volcanic. Not that long ago, actually. All you have to do is go a little bit further out west and south, and all of a sudden, you're in recently volcanic territory. You go out to New Mexico or Arizona. There's tons of little volcanoes, mostly cinder cones out there. Any of you all ever flown into the Phoenix airport? Yeah? As your plane is circling around the city on your way down to the tarmac, do you ever notice that there are these weird kind of half semicircle mountainy sort of shapes? Yeah, no, those are volcanoes that the city has been partially built around. Yeah, they're all over this area. Now, why do we have some former volcanic activity in our area? Not like we can't look outside the window and see them, but you go like down towards Big Bend, right? Most of that is volcanic rock, right? So why is all of this here? We actually have some interesting tectonic activity going on in our vicinity. The Rio Grande Rift. Do you know where the Rio Grande River is? Right? Any of you all ever been there? Huh? Yeah, it's the one that makes the border with Mexico.
I've been there.
Yeah, you've been there?
Crossed it once.
You crossed it once?
Illegally.
Illegally.
Fun.
Going into Mexico.
I went to Big Bend. I crossed crossed over for like a minute and then came back because it was so shallow.
Yeah, it's been really shallow at a
They
lot
don't
of the last
care
years.
about people crossing because there's nothing on the other side.
Yeah.
There's nowhere to go.
Yeah.
Die.
That's true.
I've gone hiking there.
You've gone hiking there? Yeah. But why does the Rio Grande River follow that particular route? Because it is flowing through what is called the Rio Grande Rift. Essentially a valley that is in the process of forming as a divergent plate boundary forms in the middle of our continent. Where the Rio Grande River is right now, the North American continent is thinning as different parts of it are pulled away from each other by new convection forces underneath of our continent. As it thins, it's going to get filled with more and more water until finally the Gulf of America is going to flood into what is now the Rio Grande Valley. And there will be an extension of the Gulf, I'll just call it the Gulf, up through North America where the Rio Grande River is right now. Give it another 20, 30 million years, there'll be an extension of the Gulf up into North America. Pretty cool. That's happening. And as that happens, some volcanic activity is going to be associated with that change. Also, in my opinion, that's a big part of the reason why we have a lot of earthquake and in addition to the artificial reasons why we have earthquakes in our area as well. A lot of the fault lines that are here for those earthquakes to occur along are probably the result of that tectonic force.
So can we like trigger volcanoes?
Ooh, good question. If a volcano has enough pressure built up inside of it, presumably, yes, we could trigger a volcanic eruption. You're thinking like a Bond villain. I love it. Okay. Yeah, so if I could tell like Mount Rainier had a lot of pressure underneath of it, and then I don't know, I set off a nuke on the top of the volcano, I might remove enough of the material up there that it no longer can hold back the pressure. And yes, there would be an eruption. You think the nuke would suffice? Yeah?
That's what I was going to say. I think they have a nuke to worry
Yeah,
about.
well, the problem is you would need to remove enough material to overcome the pressure holding down the pressure in the chamber, right? The greatest force of destruction that we have at our hands is nuclear weapons. So yeah, the nuke would probably cause enough destruction on, just by being a nuke, but then throw a volcanic eruption on top of that too. Yeah, no, that'll be it. Oh, actually, that might even make it worse because you get your nuclear weapon, kaboom, and then volcanic eruption, kaboom, right? All that ash would probably be irradiated now. So, yeah, that's like super Bond villain stuff. Not only is there ash falling all the way to Oklahoma, but it's all radioactive ash now too. Everyone's dead. Shoot! Don't do it. Yeah, it's like the worst dirty bomb ever. Yeah. Okay. Now, where you see these black triangles, that's where all our composite cones, like Mount St. Helens and Mount Rainier are. What do you notice? Where's the pattern here? Where are they? Along which coast in particular? The Pacific Ring of Fire, right? It's like that part in Finding Nemo. The Ring of Fire, right? Yeah, you know. Okay. So, Pacific Ring of Fire, we call it that because of all the earthquake and volcanic activity along its boundary. Now, we also have some composite cones elsewhere, mostly in the Middle East and Africa. The same thing that's happening here with the Rio Grande is happening here. There is a gigantic rift valley here. It's just a lot further along than ours is. As a matter of fact, give it 10 or 15 million years, East Africa here is going to be separated from West Africa. Right here where you see this valley with these volcanoes, that's going to be ocean. And that activity has made a whole bunch of volcanoes there. Now what's happening up here? Why are there a whole bunch of volcanoes around this area? Well, because Africa is currently moving north. It's crunching into Europe. Give it another 50 million years or so, there will not be a Mediterranean Ocean, a Mediterranean Sea. That's going to be gone. There's going to be a massive mountain range here to rival the Himalayas because Africa has finished slamming into Eurasia. There will be one big mega continent here, Afro-Eurasia. Yeah. We're like, what?
Africa of the Americas.
Africa of the America. I don't know what you're referencing.
America.
But America's over here.
It's out.
Oh, okay, got it. Okay.
Canada, that's just America 2.0.
America North.
If Trump has his way,
Oh.
yeah. Oh man, that's coming up a lot.
We're taking over Greenland.
I mean, yeah. Okay. Side note about Greenland.
Greenland, America.
This is a little bit pessimistic. I honestly, genuinely do not think that that's going to be a serious thing. I do not think that we will have Greenland. First of all, let me put that out there. But with our current rate of global warming changes, and with how accelerated it's going to be over the next 4 years because of choices, right? The rate of iceberg and glacial melt is going to increase, which means that really, when you think about it, in a couple hundred years, Greenland is going to be prime real estate. So it's actually, if you have no intention whatsoever of slowing down global warming, buying Greenland is actually a pretty savvy business deal. Just putting that out there. Like, buy it now when most of it's useless and covered in ice. 200 years from now, oh, everyone wants to live there, right? First of all, we are not changing the name from the Gulf of Mexico to the Gulf of America. He is. I don't know. Imperialism?
But all leaders do that. Like in Europe, every time a new king or conqueror would come into a certain place, they change the name. Like, well, what is the Constantinople?
That
whatever
Istanbul.
Sophia is that has changed names
Yeah.
over and over.
You're right. It is a common thing that conquerors do.
Yeah,
I mean, he hasn't conquered anything,
monarchs.
but
Yeah.
Huh?
I mean,
She has a point, but all of those people were monarchs.
Yeah.
Kings. or
Oh man, I
presidents.
really don't want to
Just
make
act
this
like
into a
king.
political thing. The last thing I'll say is that he signed 200 executive orders on day one. He set a record. The previous record before him was 22. That was Joe Biden. Previous record before that was 4. That was him in his first term. Okay, so he signed 200. These were a few of them. And he said in an interview, I will only be a dictator for day one. When he signed everything, right? That's what an executive order is. You can sign a law without ever having to make it past Congress. It was designed into the Constitution as a safeguard, right? We need a decision too fast for Congress to decide. We can't gather hundreds of people fast enough for this decision to be made. We need to go to war. We need to respond to something. Something needs to happen. So the president has the authority to sign an executive order. It has been drastically and terribly abused over the last 10 presidencies or so, until now we are at the point where, really, when you think about it, Congress is really irrelevant if all the president has to do is sign an executive order whenever he wants. So that's where we are. And that is quite unfortunate. Regardless of whichever political side you're on, it is very unfortunate.
That's why he was doing it all on the first day. That's the only time you could get everything in.
He could sign an executive order any old time, but he made a commitment to try and get all of the ones that he wanted done on day one without asking anyone. So here we are. America is a great and wonderful country, and I am very much a patriot. I cry during the national anthem every time. I kid you not. I go to an OC basketball game, they play the national anthem, I'm there to love America. But we have some terrible leaders in our history.
Especially
Whitney Houston's version?
Yeah,
Yes,
when
it's
she did
excellent.
the Super Bowl that one year.
Yeah,
Oh,
yeah.
that movie's probably-
Super Bowl national anthems are a crapshoot. They can be really good, or they can make you go, "Ugh," right, Marquez?
I'm really sorry to continue this tangent, but what does it mean that we're no longer a part of the World Health?
The World Health Organization. Okay, yeah, so that was one of the executive orders, was pulling us out of the World Health Organization. The World Health Organization was established as kind of a United Nations-esque sort of thing where people could unite together to pool funds to help countries, nations, communities that are struggling with things like housing and clean water. Yeah, it's basically, so it's kind of a communal pool right? And doctors work for the World Health Organization when they want to be sent to other countries wherever the greatest need is, things like that. First world countries like the United States and England and France and all of these are often the ones that are asked to foot the bill the most, because we are, in general, the richest, the better we're off. Fewer World Health Organization trips or missions have to be sent to the US because we are pretty self-contained as far as taking care of our people, than have to be sent to like Haiti or the Ivory Coast or, you know, over there, right? And so as a result, we end up paying more money than almost any other country by being part of the World Health Organization because we need the least help. And so because of that, Trump pulled us out of the World Health Organization because he believes we have been treated unfairly as a result of footing so many of the bills. I guess that depends on your world perspective. Now you've got kind of two extremes as far as American presidents go. You have people who are so America first that it's to the detriment of our relationship with every other country, which unfortunately Trump pretty much falls under the category of. Or of the other people, like President Obama, who were very much, we are so much part of the world community that it's at the detriment of the American people, right? There must be somewhere in the middle. Do we have to be one or the other? I hope not. I hope that's not always our future. I hope at some point we do have someone who's an equal balance of the two. But right now in a two-party system, everyone goes so far that way or so far this way. I get whiplash every 4 years. Yeah. That answer your question, Marquez? All right.
Would you ever run for president?
The only reason why I might say no is because I know what it would do to my wife. She has a hard enough time with me being gone as it is. I think that given the chance, anyone who thinks that they understand America should run for president. Yeah, I think anyone who thinks that they can do good should run for president. I think that I have enough understanding of the political system. I'm not a politician. I'm not an expert. But I try and live to be a good person. And I'd rather have a good person as president than someone who is skilled at manipulating other people. So yeah, I can see myself trying maybe if I ever get to that point.
I don't like the AI medical thing where they can map your whole DNA thing.
It's right now it's illegal to do anything with DNA mapping. Like it's illegal. This is something that we talk about more in 1404 where we discuss genetics. But right now it's illegal to take your DNA and do anything with it other than analyze it to give you maybe some genetic information. Like I've done 23andMe. You guys know what that is?
I want to do that.
Right. It should. It's fun. It's really cool. You figure out what your genetic history is. I'm like 23% Norwegian, and the rest of me is German and Russian, and then there's some Scottish in there, and then there's like 0.6% Neanderthal or something like that. I know the unibrow gave it away, didn't it? Right? The prominent eyebrow structure. Yes. Yeah, so stuff like that, you know, you can do that. But as far as like, I have your DNA profile and hey, I could give you a redheaded child in a lab if you want. You know, it'll look like you but have red hair. That's illegal, right? We can't do that right now. Something that we discussed more in 1404 is how we have the ability to manipulate genes, but internationally it's considered illegal. You know, someone somewhere is doing it. We've caught people doing it. There have been people arrested in labs where they actually have been trying to grow human children with customized traits, right? It's just those people are arrested and they're put in prison right now because we don't consider ourselves, the scientific community, international community does not consider ourselves mature enough to do that responsibly yet. And we don't want anyone running around with, you know, right, this is how you go down the super soldier thing. Yeah, but I mean, Winter Soldier, right. Well, you can only go so far. It's not like I can make up traits, right? I can't give the child laser vision because that child has never had an ancestor with laser vision. However, Right, right. I can't regress DNA to the point where they have. I can't change the DNA to that point. Even splicing DNA with other animal traits is beyond what we can do right now. I can, however, because I have an ancestor with blue eyes, and I have an ancestor going back millions of years with orangutan-like arms. I could make a blue-eyed orangutan armed child. Right. We can do stuff like that. If it's in my DNA, we can do it. I could give my children long, sharp teeth back from when my ancestors had that before mammals and reptiles separated from each other. That's in my DNA. We know how to do that. It's just a matter of it's not wise, and so we don't legally. Someone's probably doing it, but
What happens to the kids that are already born? Like the people that made the kid?
as far as I'm aware, no one's been born with that. As far as I'm aware, there may be Stranger Things reference. There may be little 11s running around somewhere, but I'm not aware of them.
Too late for that new season of Stranger Things.
I know, me too. I know. The problem is those kids got old, and then everyone wanted them. Everyone wanted them for every other project. Okay, I am bringing us all back to center. Okay, just for a few more slides. We're almost done, I promise. Okay. This volcanism happens along our tectonic boundaries you learned about. The convergent, the divergent, and the transform. Okay? I know that looks like a line dance move, but that's not. Okay, just remember that, because that's what I'm doing. Convergent, divergent, transform. Cool? All right. The convergent volcanism, that's where the plates subduct one under the other. The water in the mantle reduces the melting point, and then you get magma that goes up to the surface and makes those coastal mountain ranges, right? Divergent volcanism, that happens at those divergent plate boundaries between, at the mid-ocean ridges, where the new plate material is being made. And so there are volcanoes where the two plates are separating away from each other, and that's what's making that new material there. Intraplate volcanism happens when a hot spot, which is a plume of magma that comes up underneath a plate, right? In the middle of the plate. It's not at the edge, it's in the middle. What happens then? Well, it's not like it's going to stop and just wait there patiently for the edge of the plate to come around, right? No. It still chews its way up through. It might take a while because it's in the middle of a plate, but it does. Number one example of this, let me back up a few slides here, actually. Where's Hawaii? Is that anywhere near a plate boundary? No. It's in the middle of the Pacific plate. This is a hotspot. A plume has come up from the mantle and has chewed through the middle of the Pacific plate, making this chain of islands out here we call Hawaii. There's also an example on land. Where's Yellowstone? It's out here in the middle of North America, nowhere near a plate boundary. Same thing. Giant magma plume came up under North America, chewed its way up, and now we have a giant supervolcano in the middle of a tectonic plate. Okay, that's intraplate volcanism. Just like this, plume of magma coming up underneath of a plate. And then this is just something that you can use for reference to when talking about what we just did, where you have the different types of plate boundaries, different examples around the surface of our planet, and what different types of volcanism will occur in that location based upon plate interactions or intraplate volcanism. And then the last thing I want to talk about, something we already kind of mentioned earlier, how do we monitor for these things? Because we want to be very careful with making sure we get the right information to people so that they don't get hurt by volcanic activity, right? So we have lasers and satellites and temperature monitoring and all of that at all these volcanoes that we know are a danger to try and stop people from getting hurt. And it's very important that we do our best. Unfortunately, sometimes some things slip through, or sometimes people can be too timid to mention if there's going to be a problem. Because if they're wrong, sometimes people lose their jobs. Okay? All right, that's all I've got for you today. As far as the lecture goes, let me really quickly introduce you to Lab 2. Igneous rocks. Do your best to finish up lab 1 this week. I definitely want you to finish lab 1 before you start lab 2. You will not understand enough about lab 2 without having completed lab 1, getting that experience under your belt. So turn in lab 1 and then start working on lab 2. This PowerPoint here is really just a reminder of all the stuff that we talked about over the last 2 lectures, all the different textures, what they mean, what they may look like. And you've got 12 samples. Yay, you don't have 24. Lab 1 is the only one that had 24 samples. Labs 2, 3, and 4 only have 12 samples each. Okay? Yes?
Can you push the due date for the second lab?
Can I push it?
Yeah, push it back a couple days.
I have to be careful with pushing due dates because we only have 8 weeks to work with. And because I don't want you to have the lab exam and the final exam in the same week, I give you the lab exam week 7. So I can't really push things too far. If you do need some extra time on lab 2, I understand. But by needing extra time on lab 2, you'll need extra time on lab 3 and then extra time on lab 4. And it'll be additive so that you may not have even turned in lab 4 by the time you need to take the lab exam. So we need to be careful with how we do that. I don't generally take away points for a late assignment unless it's really late. I just may not grade it the same time I grade everyone else's. If I get 17 lab 2s turned in on the due date, I'm going to grade them. And if I get 3 turned in late, I may not go back to grade those until I'm doing another pass through all the other things that have been turned in late as well. Because I need to keep up with grading the things that are turned in on time because that's my commitment to you. Okay, so just bear that in mind. I understand if a little more time is needed, though. I don't pretend that my labs are easy. So I understand if you need a little bit more time. Okay? We good with that? Great. Any other questions about the lab? Every time I go back to this recording screen, I'm always paranoid that if I go back and I realize that I never actually pushed start. That's happened to me enough times that I'm like scarred. It's like, I have to do it all again. Okay. All right. Well, if there's no more questions, we're going to move into lab time.